So for this lab, we are going to demonstrate a closed-loop control system. In this closed-loop control system, we're going to use an 8-bit DAC through a power transistor that is driving a light bulb. Attached to the light bulb, we have a 10 millivolt per Kelvin temperature sensor, and that temperature sensor is going into analog 10 on the S12-UB board. So the point of this lab is to have the control system achieve a temperature that is displayed here on the 7-segmented display, as we have done in all the previous labs. So from a wiring perspective, this lab is identical to the previous two. Now, the point of this lab, again, is to let the board, that is the microprocessor, do the control for us. So we want to set a temperature in the program. And so we would then set up, right here, an equate, or that is a constant, that sets the set point temperature. Right now I've got it equated to 27 degrees Celsius. As you can see, that there's a couple other parameters as well that you will then interpret in the lab, something called offset and gain. So let's go ahead and execute this program. We'll hit the serial monitor button right here, and we'll hit go. And as you can see, the light bulb has come on really bright, because right now it's reading 25 degrees Celsius, 26, and as you can see, the light bulb backed off automatically because we are rapidly reaching our set point of 27 degrees Celsius. In fact, we have reached it already. Now you can see the light bulb is blinking on and off due to the air currents in this room. We have overshot the temperature momentarily. You might have noticed that it went up to 28. There it is again. And the light bulb is going up and down because the control system senses that. It backs off on the intensity of the light so that the temperature then tries to maintain at 27. And there it is, close to 27. It overshoots a little bit. And some of these parameters can be adjusted, such as the offset and the gain, to optimize the control system. You can see that in the lab write-up. Now we can be meanies and use a little bit of freeze spray here to make the control system respond to us. So for instance, if I begin to cool down the light bulb, you can see that the temperature is dropped and the light bulb gets very bright because the control system senses that and wants to get back to the set point. And so we're back to 27 again. So let's be mean again. Really get that cold. We're down to 24, and you can see it's at full brightness because the control system wants to get back to the set point. So we're at 25, and you can see the brightness is going up and down as the light bulb warms up again. And soon we'll be back to our set point of 27, and the intensity of the light bulb should go down markedly. And it does. Again, your results may vary, again, depending upon the gain and the offset that you use. Take a look at the lab write-up on that, and it's fun to experiment with that. And it really has a lot to do with the physical parameters of the setup, that is how tightly coupled the temperature sensor is to the heat source, as well as air currents, insulation, a lot of different aspects of the physical that is the physical makeup of the coupling between the heat source and the temperature sensor. But this is a rudimentary closed-loop control system utilizing the S12-UB board and assembly language.